All right, so good morning, everyone. We're going over Lab 7 conductivity, salinity, and desalination today. So conductivity, more water quality parameters where conductivity is one of them, where this is something that we can directly measure. Salinity, how salty a solution is, that can't be directly measured using a probe, but we can calculate that from conductivity. And desalination is the process of taking out salt or taking out pure water from seawater or salty water. So the lab outline for today is that we're going to go over salinity, conductivity, and desalination of water resources. What does that look like? What are each of these parameters? And the desalination video, which is, I'll show, it's around 10 minutes, where it shows you how you would do the process in a lab, where you would take out pure water from seawater. And that gives us a really good background on what it would look like in a wastewater treatment plant. And at the end, I'll give you an overview of the data sheet and the post-lab questions on Canvas, which you'll answer and turn in. So conductivity and salinity. Conductivity is the ability of an aqueous solution to conduct an electrical current. This is measured in units of Siemens, or capital S. This is something you can directly measure using a probe, and it's dependent upon the amount of ions in a solution. So for seawater or any salty solution, the ions for that would be from dissolved salts. And salinity refers to the concentration of dissolved salts in an aqueous solution. So how salty your solution is. It's measured in parts per thousand, ppt, or it looks like this unit where it looks, it's like a percent with an extra zero at the end. And it's not something you can directly measure using a probe, but it's calculated from what number, what value you get for conductivity. So salinity of various ecosystems, it's going to vary based on whether you're looking at a freshwater stream, looking at the ocean, looking at maybe a mix between both of those. And so salinity can be defined by different sample types. So say if you have freshwater, it would be a salinity of less than 0.5 ppt. This is actually the US public health standard for water that you can drink, that's safe for you to drink. Anything saltier than that, you can drink, but it's not good for you. And for seawater or saline water, we have a ppt of 35. And this number is like the global average salinity levels for seawater. And it's around this range, but anything between 0.5 and 30 ppts is brackish water. So a mix between both of those. And if we were going to look at, for brine is anything that's even saltier than seawater. So it's over 40 ppts. And that's sometimes byproducts of, most of the time byproducts of desalination is going to have brine that's over the global seawater 35 ppts. So if we were going to look at California, we can see that there's our ocean on the side, our bay, and there's this, from here, our Central Valley, Sacramento, and San Joaquin rivers is going to give us fresh water, inland from freshwater, and it's going to come down and mix in the bay. So around Ocean Beach, you see how it's not quite as dark as the ocean. This water here is this mixing of freshwater and seawater. So that's brackish water. And it's not going to be as salty as our ocean water, but it's not going to be as low in salinity as fresh water. So this is one example of brackish water that we can see just right in the bay. So one way that we can do desalination is through distillation. So distillation is this process that we can do in lab where we have our hot plate and our Erlenmeyer flask holding our seawater, and we have a couple of boiling chips. Boiling chips look like little pebbles that if you put it in your flask, it helps your solution boil. We have our clamp to hold our Erlenmeyer flask in place, our stopper, which connects our glass tubing or rubber tubing to have like whatever we're condensing in the collection vial at the end here, which is like being held by a beaker with either tap water or an ice bath. And what basically happens is that through this hot plate heating up our seawater is going to, or pure water is going to evaporate and is going to be collected and transferred through glass tubing and condense again in our collection vial. Where if we had our ice bath or just a beaker with tap water, it's going to recondense and show up here. So one thing we do want to note is that we don't, in lab, we would want to make sure that the glass tube is not too close to the distillate at the end here. So we would try to make sure that there's enough space for the water to collect, but the glass tubing, rubber tubing, whatever it is, it's not too close to the bottom, where this whole process takes around 20-30 minutes to collect our pure water at the end. And we wouldn't want it to suck all the water back in, because if it's too close to the bottom, it's going to create like a vacuum, and all of your work for the past 20 minutes would just go right back to your Erlenmeyer flask. Yeah, and it like makes a loud noise too. It's not dangerous, but it could scare people. So that's one thing in lab. We would want to make sure that the glass tube, rubber tube, whatever, is not too close to the distillate. So what do you have after distillation? So before distillation, we have our Erlenmeyer flask with our seawater, and we have our vial with nothing in it so far. After distillation, after we've boiled our water, after our pure water is evaporated from the seawater and it's collected in our distillate, we have brine left over in our Erlenmeyer flask, which is this salinity of greater than 35 ppts. Before distillation, we have our seawater of salinity where it's around like the global average of 35 ppts, but after all of the pure water has been taken out, it would be a lot saltier. So we have our brine in our Erlenmeyer flask and our distillate, our H2O, our water, our pure water, in our vial. So at the end, we would have our brine, which is hypersaline, super salty, and our fresh water. So this video is going to walk you through what it would look like to do the distillation process in lab. It's also on your Canvas page. It's around 10 minutes, but there's some differences between how we would have done it in USF. Like they use Bunsen burners, we use hot plates, some differences in units, but generally everything is pretty much the same how we would do it, like the concepts are the same. But yeah, I will now play this video for you all and we can see what it would look like in lab. Okay.
Over 70% of the Earth's surface is covered with water. But most of that water is salt water in the oceans. Only a very small amount of that water is actually fresh water, and most of the fresh water is locked up as glaciers. And some of it's in our lakes, and only a very small amount is in our streams and in groundwater, and that's the water that we rely upon as drinking water. The leading cause of death of children in the world is lack of clean water. So can we take salt water and turn it into fresh water? That's the purpose or objective of this lab, to take salt water and run it through a process called distillation and distill it into fresh water. Process of distillation is very energy intense. We're going to need a Bunsen burner for this lab. We're going to need obviously a lighter to start the Bunsen burner. You'll need a 250 milliliter Erlenmeyer flask with a rubber stopper and a tube coming out of it that's going to collect the steam, and you're going to need a test tube in order to condense the steam into liquid water. You'll need a 600 milliliter beaker, some ice, a couple boiling chips or rocks, LabQuest device, and a conductivity probe to measure how much salt is in the water. And of course you'll need salt water in order to run this experiment as well. To your 250 milliliter Erlenmeyer flask, go ahead and add a small handful of rocks. And those are going to be boiling chips that are going to allow the salt water to boil at a normal amount without overboiling. To the Erlenmeyer flask, also add 100 milliliters of salt water. Replace the cap on the Erlenmeyer flask. Make sure that the tube, the rubber tube, is going to travel continuously down without having a bend or a kink in it where the water can start to build up. That can be kind of dangerous, so make sure it's a normal line going all the way down into a test tube, which is and this test tube has to be extremely clean because you're going to be collecting clean, pure distilled water, so make sure that this is very clean. If not, make sure to rinse it out a bunch of times with distilled water and collect it in a 600 milliliter beaker that contains an ice water bath. So this beaker should contain ice and water to make an ice water bath. Okay, so there's your ice water bath. Go ahead and put the test tube in the ice water bath. Before you start the experiment, you're going to want to measure how much salt is in that water. I made up the salt water to contain 8 grams per liter. Now let's use our conductivity probe to measure and see how much exactly is in there. Plug your conductivity probe into the LabQuest device. Over a towel, rinse the conductivity probe with distilled water. The tip of the conductivity probe, the very end of it, rinse it with distilled water. Only ever use distilled water. If the distilled water ever runs out, make sure to only fill it up using the distilled water in this container and not to fill it up from the sink, so that these always only contain distilled water, purified water. Place the rinsed conductivity probe directly into the salt water. Make sure that the tip of the conductivity probe is completely submerged. Right now it's not, so what I need to do is tilt this a little bit so that the conductivity probe is completely submerged. Make sure the toggle switch on the conductivity probe is on the 0 to 20,000 reading. This is because we're measuring salt water, and salt water is going to have a high reading. So we're not going to use either the lower readings, we'll use the highest reading. On the LabQuest, change the units to milligrams per liter. Change the units to milligrams per liter. I said before that I made this salt water as 8 grams per liter. That would be 8,000 milligrams per liter. This is reading 7,215. That's probably pretty accurate. Simply record the live readout in your data table. So I would write 7215 milligrams per liter in my data table. You do not need to connect your iPad to the LabQuest for this experiment. Carefully remove the conductivity probe from the salt water. Over a towel, rinse the salt water off the conductivity probe using distilled water. Set the LabQuest aside. You won't need it until you've completed the experiment. Reset your Erlenmeyer flask. Put the cover back on. Put on a sweet pair of goggles. Now it's time to light and adjust your Bunsen burner. So the first thing you want to do is connect the Bunsen burner tube to the gas. Turn the valve on. Go ahead and light your Bunsen burner. So this flame looks pretty good, but I'm going to show you how to make a couple adjustments in case it doesn't look so good when you first turn it on. First of all, I'll show you that there's 2 adjustable things you can do. One is that you can turn this, and by turning that it's going to reduce or increase the amount of oxygen that's going into this thing. Alright, so if you find a really orange flame, this is what you need to adjust. You need to adjust the base here. Get it back down so you have basically a flame within a flame. You've got the inner blue flame and the outer blue flame, and should be about a 1-inch flame there and about a 2.5-inch flame there. If you're not getting enough flame, you can do one of two things. You can make this adjustment on the base here. Maybe that's it. Maybe that's reducing how much gas is coming out. By increasing this, you're increasing how much gas is going through, and that's way too much. Again, you just want kind of a normal flame there. So again, that looks pretty good. I'm going to be happy with that. Just wanted to show you some adjustments quick on the Bunsen burner. Go ahead and begin heating your salt water, making sure that everything looks good. Okay, this tube should be going all the way down without any kinks in it, all the way into your clean collection test tube, which is in the ice water bath. You want kind of a nice medium controlled flame so that things don't get out of hand. If they do get out of hand and this boils over too much, you're going to contaminate your test tube, and what you're going to want to do right away is if things get out of hand too quick, the first thing to do is probably just to move the Bunsen burner out from underneath the flask. Then obviously you can start taking time and making adjustments on the flame. So things are going pretty well. I've got a pretty good rolling boil here. Just be careful that you don't want it to boil all the way up to the rubber stopper, or you're going to start to get salt water in there. So again, you can make some minor adjustments on the flame to make sure to keep it down, so that you're not going to get too hot of a boil, just a normal boil. You can see I'm kind of zooming in on the test tube inside the beaker, that you can see that the level is rising. I'm collecting distilled water as it boils here, slowly but fast enough that you can observe it happening here. And we're condensing the steam into water here in the ice water bath. Again, just be very careful. This is a potentially dangerous situation, so please just don't sit on your iPad and play games. Obviously, you'd never want to do that, but this is something you need to keep an eye on here. We got very hot steam, we've got boiling water here, we've got a potential pressure situation if this gets backed up, so just make sure you're monitoring this the entire time it's happening. When it looks like you've got enough distilled water collected in your test tube, go ahead and shut off the flame by turning the valve off. Don't just blow it out here, the gas will still come out. Now what we really want to do is get a reading on what's the conductivity of the distilled water. So again, you might burn yourself if you grab that, just be careful. And we want this to be in room temperature water, not ice water, so I grabbed another beaker. I'm going to fill that up with, carefully so that you don't burn yourself, transfer your distilled water into that room temperature water. When a few minutes have gone by, place the conductivity probe inside the distilled water test tube. Since we're reading distilled water, you really need to change this setting. Okay, so this should no longer be 0 to 20,000. We're checking distilled water. That's probably going to be a pretty small amount of salt in there. I'd probably change it to the lowest setting, which is 0 to 200 for this reading. Make sure that your units are in milligrams per liter. And I'm now reading 11.5 milligrams per liter, where we're reading in the 7,000s before. So yeah, we definitely purified and distilled the water, the salt water, and obtained some very fresh, pure distilled water. Clean up, make sure to rinse off your conductivity probe one more time and dry it off before you put it away. Like always, rinse out test tubes and beakers. I just recommend at least rinsing them thoroughly 5 times to make sure you get any salt or anything like that off of them. Certainly allow your Erlenmeyer flask to cool for a long time before you touch it. Please take your time cleaning up lab equipment, rinsing off glassware, and spraying off your table. Thanks.
Okay, so the process for desalination through this video is pretty much exactly the same, just few minor differences. They have Bunsen burner, we were going to use hot plates. The units that they put at the end was milligrams per liter, but the probes in the lab can also just give you the units of microsiemens, and that is perfectly fine. That's what we're going to be using. That's the units that we'd be using for our measurements today. And they have iPads and we don't. So little differences like that, but the overall concept's the same. So, well, is desalination the answer to drought? if this process can be done, then why don't we do it then? Why don't we just desalinate our water and get pure water and then address, water needs? So there are proposed plans for desalination plants in California, and there is a desalination plant in San Diego at the moment, but plans are in place, but is it the answer to drought? So we can try to answer that by first looking at the process of desalination in one of these plants. So first we have our seawater, and it's going to go through pretreatment. So pretreatment is when water is filtered for different particles, for different sediments, bacteria, anything that you can take out in the initial step before you would have to put it through the desalination process. So in pretreatment, all of the solid waste, all of these extra particles that are taken out, you would take them to the landfill, and then the remaining water you would put through our desalination step, where basically that water is forced through filters, which uses reverse osmosis, and it just forces your water through all of these different filters, and it takes out most of the salt. And then at the end of the process, like in the lab, we have our brine, which is going to be this hypersaline, super salty solution at the end. And so what you have at the end with brine, you would then either mix it in with wastewater or other like seawater before you put it. If you mix it in with seawater, you would like put it back into the ocean. If you mix it in with wastewater, you would put it through treatment again. And then but that's at the end. We still have our brine, super saline, hypersaline. We can't put brine exactly as is, like that in its super salty state back into ocean water, because it would affect the ecosystem and the organisms that aren't used to how salty that is. But then along with brine, we have fresh water, which will then go through post-treatment. So post-treatment is when water is chlorinated through desalination and pre-treatment. Minerals and ions are taken out, so you would add them back in either for taste or because it's not really healthy to only drink deionized water over time. You can drink water with no ions in it, but it's you can't really drink it for a long time though. So minerals are added back in for taste and for nutrients. And then in post-treatment, other things can be done too. Like there's also UV treatment that your water can go through, but post-treatment is just water chlorinated. You're treating your water before you store it and deliver it to people who need it. So this is the process in a desalination plant. So distillation that we saw in the video is separating water, pure water, from salt by boiling point. So when you boil your seawater, your saline, your salty solution, through evaporation, your pure water is going to evaporate, transfer, and then recondense in your collection vial. Some pros to distillation: we have a lot of seawater. If you're near a coast, you have a lot of access to seawater. It's a relatively straightforward concept. Distillation, as we saw in lab, can be transferred and used in a plant, and that process can be done in a water plant. Some cons is that it's really only limited to coastal areas. If you're too far inland and you don't have a steady access of seawater, it's not really a viable option for you. It does require a lot of space. So that process that we saw on the last slide, all of those different steps is going to take up a lot of space, and it also requires a lot of energy. So say instead of treating regular wastewater like catchment or rainwater, if you wanted to do this process, it would take 200,000 times the energy of instead of just regularly like treating regular wastewater that we would get. And it also produces a lot of brine, so that super saline, super salty solution at the end. And that would have to either go through another treatment process before it can be released back into the ocean, or you would have to, it just impacts ecosystems, so you can't directly just release it back to the ocean without treating it first. So why are ions important in drinking water? When they're taken out of water, why do we need to put it back in? So it's not really healthy to drink deionized water as is for a long time. You can, it's fine, but you do need, your body does need ions for a lot of different functions, which include conducting energy, transporting nutrients, supporting mental function, converting calories into energy. And yeah, you do need ions in your water, minerals in your water. That's why if you think about bottled water, if you look at bottled water, sometimes on the label it says minerals added back for taste. Or that's when, after they go through the process, they add back your nutrients in either for taste because it doesn't really, it tastes, you can notice the taste if there's no ions in it. But also that's why if you look at bottled water, there's that nutrient label. And that's why there are nutrient labels on your bottled water, is that they add back nutrients into your drinking water. So, but now if we think about, well then, or like the different organisms that can drink seawater, there are a handful of land terrestrial animals that can drink seawater. And one of them is the seagull. And well, how can seagulls drink seawater? It's they evolved so that they can actually. So whenever they drink seawater, they have a gland above their eye that collects salt. And when it's full, they would just shake their heads and then they would just excrete out of their eye. And this is one of the terrestrial animals that can drink seawater. Another is like this iguana from the Galapagos, where after they drink seawater, they can sneeze out the salt. And yeah, there's a couple of them that can. And yeah, these are some. Now I can just show you the data that you'll be using. So if we go into our Canvas page, and we have this main page here. For lab 7, we have our desalination, distillation video link here, and our lab 7 assignment data and questions handout is right underneath it. We just click on that. This is going to give us the data that we'll be using today. So we're given 2 different tables. Table 1 is conductivity, salinity, and temperature. So that is that video. This is the data from the video that we saw, that process of doing distillation. But this is data that was collected in a past like ENVS lab, where we have our seawater before distillation, and the salinity for that is 27.2 ppt. We might be wondering, why isn't it 35 ppts, like the global average seawater salinity level? It's because this seawater is from Ocean Beach, where it's that mix between fresh water coming down from Central Valley and the Sacramento River mixing in with ocean water. So it's this brackish water where it's not as salty as seawater, but it's not to the salinity levels of fresh water. So that's why it's 27.2 ppts. And then we take this Ocean Beach water, put it through distillation. And at the end, we have our distillate, our pure H2O, our pure water, and the salinity for that is 0 ppts. And the brine that's left over in our Erlenmeyer flask, after distillation, it's going to be more salty than our seawater in the beginning because all of our salts are left over. So that's 39.1 ppts. Then we have conductivity at the end, this next column, and then temperature right over here. That's our table 1. For table 2, we measured conductivity. We have data for different sample types. So we have this very first is seawater from Ocean Beach. We have lake water from Lake Merced, tap water, and deionized water. So deionized water is water that's most of the particles, most of the ions are taken out, and you do this using a machine in lab. And deionized water can be used for a lot of things, either for washing your lab equipment or rinsing out test tubes or setting standards. So for the, for even for like a couple of different processes or a couple of labs before, we would use deionized water to set standards. So deionized water, this is what the salinity is. So we have our salinity in this column, conductivity, and temperature. And these are the two tables you would be referring to for the questions that you would answer on the next page. So in the next page, this very first question, in your own words, describe a couple of sentences the distillation procedure you use. So the distillation procedure is that video that we watched together, and you would write maybe a short paragraph, a couple sentences on how, what are the materials you need, how do you do the process, what do you get at the end. For question 2, is there a difference in salinity between tap water and deionized water? Calculate the difference using the data that was gathered. So is there a difference? Short answer is yes. So for question 2, we are referring to table 2. So salinity between tap water, deionized water. So deionized water, salinity of 0 ppts, tap water, 0.04 ppts. There is a difference. How do you calculate it? You just subtract the numbers against each other, and that's the difference. And the process is the same for question 3, where we're looking at conductivity between tap water and deionized water. Look at table 2, those two values, calculate that if there is a difference. For question 4, how does your measured salinity for ocean beach water compare with the global average value for seawater, where the salinity is 35 ppts? So you can talk about the mixing of fresh water from Central Valley and the Sacramento River with ocean water in the bay. So Ocean Beach is this brackish water. Question 5, comment on the drinkability of water you obtain by distillation. This is referring to table 1. The public health standard for water is 0.5 ppts for salinity. So is it drinkable? Talk about that. You refer to table 1. And for question 6, what is the salinity of the water remaining in the flask? So the brine in the Erlenmeyer flask, the brine that's left over, what's the salinity of that? And is there a difference from that to the initial salinity of seawater? So our seawater that we used before we boiled it, and is there a difference? You can calculate that using the data in table 1, and that's more subtracting. Did anyone have any questions about the assignment that you have to turn? You would just type this up in a separate Word doc and then turn this into Canvas. Okay. If not, then that is basically the end of lab. And you can email me any questions. It's not due until next week when we meet for lab, but if not, I hope you have a good rest of your day, rest of your week, and I'll see you next week.
Thanks, Maggie.
Thank you.
Thank you, Maggie.
Thank you.
Thank you.
Thank you.